Hello, I am Jacobo de Uña from the University of Vigo in Spain, and today I want to tell you about this joint work with Ingrid van Keilengon on Efron-Petrosian integrals for doubly truncated data with covariates. So, with doubly truncated data, the target variable, say x, with cumulative distribution function f, is observed only when it falls within two random limits, u and v, and these capital UV are called the truncation variables. And one is able to observe the values of u and v too. So at the end, we have n triplets, x1, u1, v1, xn, un, vn, but subject to this condition here. And it is very important to realize that in this setting, the distribution of an observed value of x, x1, say, is not the distribution of x in general, because it equals the conditional distribution of x given u less than x less than v. So in this setting, ordinary non-parametric estimation approaches are in general inconsistent. So this is my motivating example, is study on Parkinson's disease, in which the goal was looking for association between genetic information and the age of onset for Parkinson. The main variable X is age at diagnosis, and the sample of individuals in the study were the individuals with a blood sampling to get the genetic information at maximum 8 years later than the onset of Parkinson's disease. So in the sample, we indeed have this double truncation condition. And this is an example with medical data, but the problem of double truncation appears in other fields too, for example, in astronomy, in survivor analysis, epidemiology, reliability engineering, economics, etc. And under independence between the truncation limits and the variable of interest, x, Efron and Petrosian in the JASA paper in 1999 introduced the non-parametric maximum likelihood estimator Fn for f. And in a sense, this Fn is a correction of the ordinary empirical cumulative distribution function to take the double truncation into account. So in order to illustrate the huge difference which may occur in practice between the non-parametric maximum likelihood estimator by Efron and Petrosian and the ordinary empirical cumulative distribution function, I show in this left panel both estimators. So the black line is Efron Petrosian and the red line is the ordinary. And you see that the ordinary clearly underestimates. And this is explained from the fact that right plot, the relative chances of observing small ages of onset are very, very small compared to the chances of observing any other value for the age at diagnosis. So this figure indeed is estimating this probability of observing a particular X value because of this double truncation. So you see, it is very, very important to take this double truncation phenomenon into account in order to construct consistent estimators. But my setting is a setting with covariates. So besides X, U, and V, one observes a vector of covariates Z, which in the Parkinson's disease study is the genetic information. So Z may contain, in practice, numerical, categorical covariates, discrete or continuous, etc. So it is, our approach is completely general to this regard. And our goal is to estimate this general functional appearing here, which is indeed a mathematical expectation. It is a mathematical expectation of a general transformation of X set. And this has many, many applications in statistics, for example, to correlation and covariance analysis, to the estimation of regression coefficients beta in regression models, for example, under the linear regression model, where M is a linear function, or under the proportional hazards model. So these functionals appear. Also to the estimation of cumulative incidences for competing risks, so many applications. And the estimator we analyze in this paper is what we call an Efron-Petrosian integral with covariates. And it is basically a weighted average of the transformed data, where the weights are given by the jumps of the non-parametric maximum likelihood estimator pertaining to the X variable. In the particular case in which there is no truncation, and this is obtained for a constant probability of sampling X, so these jumps reduce to 1/n, so this Efron-Petrosian integral indeed is an ordinary sample mean. But in general, of course, it is much more complicated. And our K contribution is deriving asymptotics for this estimator under the independence assumption between the truncation limits and the target. So this is one of the main theorems in our paper, and there are several assumptions I will discuss in a minute. We have that the Efron-Petrosian integral with covariates is weakly consistent for any integrable function phi, and if in addition phi is square integrable, we have an asymptotic representation for the estimator as a sum of zero mean IID terms plus a negligible remainder. And from this result, of course, we can easily obtain distributional convergence, for example, which is needed for the construction of confidence intervals and so on. And so this is a very important result in practice. And what about the needed assumptions? Well, they are quite technical, but basically what I want to say here is that the assumptions are only slightly stronger than the minimal for identifiability of the involved distributions. And yes, we need a slightly stronger version of that because of the sort of technical proofs we use. And these assumptions ensure, for example, that the sampling probabilities, the theoretical sampling probabilities for X values and for couples UV of truncation limits are bounded away from zero. And this is needed in proofs because we need to deal with some risky denominators. And what about the proof? Okay, we derive some preliminary results that are preliminary but are interesting in their own right. The first one is indeed an asymptotic uniform IID representation for the Efron-Petrosian estimator itself and its weak convergence. And this is cumbersome because the estimator FM has no explicit form, so it is only implicitly defined. So we prove invertibility and boundedness of some linear operators appearing in the implicit representation of the estimator. We need to analyze some non-standard Volterra structures which are related to functional analysis. And also we applied some technology from empirical processes. And related to the existing literature, there are some other previous contributions to the study of the asymptotic properties of the Efron-Petrosian estimator. For example, the paper by Zheng in the Annals of the Institute of Statistical Mathematics in 2010, but with important gaps in the proofs and inconsistencies. And we repair all these inconsistencies in our paper. And the second preliminary result we needed was, again, obtaining an asymptotic uniform IID representation and the weak convergence for a second process, which is related to the first one, to the Efron-Petrosian estimator. This process AN of X is depending on Fn, and it is very important because it appears in this representation, this useful representation of the Efron-Petrosian integral with covariates. This is the denominator here, is this process evaluated at each xi point in the sample. So it was critical in the proof to have this asymptotic IID representation for this process and the weak convergence too. And at the end, we arrive to a U statistic, a complicated U statistic, to which we apply the Agit projection technology in order to finally obtain the IID representation for the Efron-Petrosian integral. So if you want to know more about these technicalities and the applications of our main results, I invite you to download our paper, which is now in press in Bernoulli, from the journal website. If you are unable to do it, please email me and I will be happy to send you the paper. And here I am also mentioning a recent paper I have uploaded to arXiv with a review of existing R packages to deal with doubly truncated data. So if you are interested in applications and in the 16 software, this second paper can be very interesting to you. Please download it. And I also announced a forthcoming book to appear in Wiley next year with titled The Statistical Analysis of Doubly Truncated Data with Applications in R. And this is a joint project with my colleagues Carla Moreira and Rosa Maria Crujeiras. So as mentioned, please contact me in case of having questions, comments, or if you want me to send you these papers, I will be happy to do it. So thank you very much for your attention and have a nice day. Bye-bye.